Ancient construction failures and their technical lessons. What if the greatest engineering feats of antiquity, the bridges, towers, and dams that represented human ambition, were not only architectural achievements, but also fail-safe lessons? What if there was a tale of error, adversity, and ultimately insight hidden beneath each magnificent ruin? Humanity's desire to construct structures that are larger, taller, and more powerful has frequently come at a cost throughout history. Towers have slanted, stones have cracked, and rivers have gorged powerful barriers, but every collapse taught us something. Through a historical trip, we examine ancient building failures and the technical lessons they left behind that continue to inform contemporary engineering. Sad el-Khafra, Egypt, 2650 BC, the dam that couldn't hold. Our narrative starts more than 4,500 years ago in the ancient Egyptian deserts, not far from Cairo today. One of the first attempts at large-scale hydraulic engineering was the Sad el-Khafra Dam. It was constructed during Egypt's Old Kingdom in 2650 BC with the intention of controlling the flash floods of Wadi Garawi, a dry riverbed that may turn into a raging stream following intense rainfall. Built of stone and rubble masonry, the edifice was 14 meters high and more than 100 meters long, making it gigantic for its day. However, disaster struck before it could ever fulfill its function. Before the dam was even completed, it was totally demolished by a sudden and strong flood that swept through the wadi. The ruins that are visible to us today, giant rocks strewn across the desert floor like bones, tell the tale of how nature's wrath met ancient ambition. What went wrong? The Egyptians, who were experts at building temples and pyramids, were unaware of the sheer power of floodwaters. When the wadi filled, the dam's lack of a spillway and outlet for extra water meant that the mounting water pressure had nowhere else to go but through the dam itself. The abrupt hydraulic stress was simply too much for the stone embankment to bear. Even the strongest structures are only as strong as their capacity to withstand the harshest conditions of nature. The first dam in Egypt might have been spared by the overflow systems, flood control measures, and adjustable safety margins that modern dam engineers create. In many respects, the Sad el-Khafra ruins mark the beginning of our knowledge of hydrology and structural resilience, as well as humanity's earliest lesson in hydraulic failure. The Leaning Tower in Pisa, Italy, AD 1173. Time travel to medieval Italy, which is around 3,000 years ago. Proud builders in the tiny Tuscan city of Pisa started construction on what was supposed to be a magnificent bell tower, a representation of both religious devotion and civic pride. Strange things started to happen, though, as the Leaning Tower of Pisa rose from the ground. The tower began to slant. In 1173, work started on soft ground, made of shells, sand, and clay. The foundation was built on unstable and compressible earth and was just 3 meters deep. The tilt was already apparent when the builders arrived at the third story. Instead, they kept going in the hopes of correcting the lean by constructing higher floors with one side being taller than the other. The issue was simply worse by their response. The tower shifted and leaned farther over ages. Construction was repeatedly stopped and restarted due to wars, weather, and time, which caused the soil underneath to settle unevenly. The tower nearly collapsed as it slanted over 5 degrees by the 20th century. What caused it to fail? The cause of one side sinking is differential settlement, which occurs when the earth beneath a structure compresses unevenly. The sciences of soil mechanics and geotechnical engineering, which would not be developed until the 18th and 19th centuries, were not yet understood by the builders of Pisa. Their error was in the foundation design rather than the craftsmanship. A structure's fate is as much determined by the ground underneath it as by the materials above it. To avoid settlement problems, contemporary engineers today carry out comprehensive soil testing, load-bearing analyses, and deep foundation designs. Paradoxically, the tower's weakness contributed to its notoriety. It now stands as a testament to how human ingenuity, with a little assistance from contemporary stabilization techniques, can save even our most faulty creations, rather than as a symbol of failure. In Narni, Italy, 27 BC, the Bridge of Augustus is the bridge that fell. In the heyday of the Roman Empire, engineering was closely associated with Rome. Awe is still evoked by the accuracy and tenacity of the roads, aqueducts, and bridges that united continents. Even the Romans, who were experts in arch and stone, could fail. The Bridge of Augustus was a magnificent stone arch bridge constructed in 27 BC in the ancient Italian town of Narni. Its four enormous arches, which crossed the narrow river, were a display of Roman ambition and technical skill. However, only one of those arches remains now. The remaining ones fell centuries ago due to floods, earthquakes, and maybe structural flaws. A basic point is brought up by the bridge's partial ruin. How could such accomplished builders have made a mistake? Narni's topography presented particular difficulties, but the Romans perfected the arch their bridges and aqueducts endured for millennia. Without adequate scour protection or deep enough foundations, the structure gradually collapsed as the river's flow destroyed the piers. When a structure's relationship to its surroundings isn't properly understood, even the most exquisite design can break down. The Romans constructed for strength, but they did not yet take dynamic hydraulic loads or long-term river erosion into consideration. To address those precise issues, contemporary engineers employ geotechnical analysis, reinforced materials, and ongoing inspection. Nevertheless, the surviving arch, which is bold and alone, serves as a reminder that each span that falls teaches the builders of the future how to rise higher and endure longer. Hatshepsut's mortuary temple, Egypt, 15th century BC, the temple that sank. In the cliffs of Deir el-Bahari, near Luxor, sits one of the most remarkable temples of ancient Egypt, the mortuary temple of Hatshepsut. It honors one of Egypt's rare female pharaohs and is a work of symmetry and elegance carved into the rock face. However, underneath its majesty is a tale of subtly flawed engineering. The geological instability of the nearby cliffs caused portions of the temple to crack and shift throughout the ages, not because of shoddy construction. The builders had cut straight into shale and limestone, a type of sedimentary rock that was susceptible to temperature and moisture fluctuations. The stability of the temple was threatened as the cliffs began to fracture due to the expansion and contraction of the stone and the infiltration of groundwater. Although the ancient Egyptians were skilled stonemasons, they lacked the tools necessary to assess the impacts of groundwater and long-term geological movement. By stabilizing the temple's cliffs with drainage systems and strengthening it with concrete, contemporary restoration workers have learned from these historical mistakes. It serves as a reminder that even beauty must submit to the laws of nature, and that knowledge of the ground itself is essential to long-lasting architecture. The city that sank, the power of the sea in Alexandria's lighthouse. The Lighthouse of Alexandria, one of the 7 wonders of the ancient world, captivated the imagination more than any other ancient building. For generations, it led ships securely to port on the island of Pharos, rising more than 100 meters above the ground until the sea took it. A sequence of strong earthquakes that occurred in the area between the 10th and 14th centuries knocked down the lighthouse and buried a large portion of ancient Alexandria under the Mediterranean. Massive stone slabs scattered across the bottom were discovered during the 20th century archaeological dives. They were the broken remnants of a wonder. The fall of the lighthouse also exposed flaws in seismic design and load distribution, even though earthquakes are natural occurrences. The construction was susceptible to lateral ground motion because of its enormous weight, which was concentrated on a small foundation on top of an unstable island. 2 fundamental concepts of contemporary earthquake engineering are that structures must be built to resist dynamic forces and disperse stress. In order to mitigate seismic concerns, modern architects employ flexible materials, base isolators, and dynamic modeling tools that the Pharos builders could never have envisioned. But for engineers as well as sailors, the Lighthouse of Alexandria continues to be a representation of light. A scientific curiosity about how the planet moves and how humanity must adapt was sparked by its fall into the water, rather than the end of a wonder. Ancient engineers pushed the boundaries of what was feasible everywhere, from the Mediterranean coast to the Egyptian deserts. And in doing so, they frequently stepped over the imperceptible line separating success from failure. However, something priceless was left behind with every collapse, crack, and dropped stone: knowledge. The Sad el-Kafara Dam taught people to honor the force of nature. We learned to comprehend the ground beneath our feet via the Tower of Pisa. The risks of erosion and poor foundations were made evident by the bridge at Narni. The Lighthouse of Alexandria illustrated the merciless power of seismic motion, while the temple at Deir el-Bahari issued a warning about geological instability. These timeless teachings collectively serve as the cornerstone of contemporary civil engineering. They serve as a reminder that failure is the path to growth rather than the antithesis of it. Every modern dam, skyscraper, and plan is based on the bones of buildings that once collapsed, as well as years of trial and error. If you enjoyed uncovering the hidden stories behind history's greatest construction failures, don't forget to like, subscribe, and hit the bell icon, because there's so much more to learn from the ruins of the past.